Hello, we are Red Planet Robotics, and we're really excited to be the first Virginia Tech team to enter the University Rover Challenge. Our 12 team members are situated across 4 different sub-teams: the mechanical team, the electrical team, the software team, and the science team. We're super proud of what we've done, and we're really excited to show it off. Here we go.
For our arm, we focused on a simple, lightweight design. To achieve our lightweight design, we used carbon fiber tubes for the majority of the structure. For actuation, we're using linear actuators for the main parts of the arm and dynamixels for wrists so we have continuous rotation. Our end effector uses a simple clamp with a 3D printed compliant insert for maximum gripping of odd-shaped objects. For our wheels, we went with a NASA-inspired design. We use a super elastic nickel titanium alloy that can go up to 10% strain without plastic deformation. This gives us a durable yet compliant wheel. For grip, on the exterior of the wheel we have chainmail, which also gives us some structure. We were inspired by a novel Swiss design for our suspension. The design allows for the ability to traverse large obstacles while maintaining maximum ground contact. The suspension consists of 2 parallel bogies on either side of the chassis with a spring-loaded 4-bar linkage in the front, and the rear suspension is fixed to the chassis.
Our main power system can be divided up into 2 main elements: the battery packs and the battery management system. For our packs, we decided to use LG MJ1 18650 cells held together with Brusen caps. Our packs are being monitored by an Orion Junior battery management system. This device will gather data from voltage tap lines, thermistors, and a current sensor, and will safely monitor our pack's charge and discharge cycles. It will also communicate a plethora of battery data to our central computer via CAN bus. We have designed and manufactured 3 printed circuit boards for use on our rover. Our first is our power board, which has 4 board mount DC to DC converters on it to power various subsystems on the robot. The second is our motherboard, which serves as a hat to a Raspberry Pi 3. This board is in charge of basic rover health. It interfaces a CAN bus converter from our RPi to our battery management system. It has thermal management for hotspots on the rover, and it interfaces to our third board, the peripheral board.
Our peripheral board utilizes a PIC32 microprocessor to receive data from our gas sensors and mini spectrometer. It also controls the dynamixel servers, stepper motors, and linear actuators incorporated in our arm design. The peripheral board also receives commands from a Raspberry Pi through a UART connection from the motherboard.
The science package contains several environmental sensors as well as a spectrometer. The environmental and atmospheric sensors include a volatile organic compound sensor, a carbon dioxide sensor, and a UV radiation sensor. The spectrometer is a Hamamatsu mini spectrometer with a tungsten halogen light source. It can detect wavelengths into the near IR region and will be used for soil component identification. As far as off-rover analysis, a gram stain will be performed to find biological evidence, and XRF or X-ray fluorescence spectroscopy will be used to analyze rock compositions more thoroughly.
For our sensors, we're using a GPS, IMU, and stereo camera. These will let us tell where we are in the field, gain state information of our rover, and detect obstacles that are in our way. To integrate all this together, we have chosen to use ROS and OpenCV. This allows us to utilize already written and tested software to use the information from our GPS and IMU and put it into an extended Kalman filter, and be able to control actuators and motors simply. We are using OpenCV during the Autonomy Challenge to be able to track tennis balls to reach our goal. We were then able to focus on piecing together the software system as a whole. For the base station, it is running Ubuntu and uses ROS to display the information coming back from the rover. It displays video feed, rover location on an offline map server, and state information to help operate the rover effectively. We also wrote a custom graphical user interface which displays the current state of our ROS nodes, allowing for quick and easy debugging. We have already tested our software on an existing robot platform. This allowed the team to be able to work in parallel with mechanical development and verify our controller and communication system operated correctly.
Coming into this competition, we realized that communications is one of the most important aspects of our design. We spent a large portion of our research looking into different communication systems and decided to test a 5.8 and a 900 MHz ubiquity system. After testing, we realized the 900 MHz system outperformed the 5.8 in both range and reliability. We also decided to pick circular polarized antennas for the ability to reject multipath interference when we have non-line of sight range with the rover.
We'd like to thank our sponsors and our advisors for helping us get this far. We're excited to be a part of the competition. Thank you.